Welcome to our webcast, Industrial Internet of Things and Industry 4.0, Overview and Practical Advice for Today. I'm your moderator, Mark Hosky, and I'm happy to join you today on behalf of Control Engineering, Plant Engineering, and Oil and Gas Engineering. And now a bit about our speakers. Dr. Richard Mark Soley is Executive Director of the Industrial Internet Consortium, and also Chairman and Chief Executive Officer of OMG and Executive Director of the Cloud Standards Customer Council. In 2014, Dr. Soley helped found the Industrial Internet Consortium to accelerate the development, adoption, and widespread use of interconnected machines and devices, intelligent analytics, and people at work. The members of the IIC catalyze and coordinate the priorities and enable technologies of the industrial internet. Dr. Soley also serves on numerous industrial, technical, and academic conference program committees and speaks on issues relevant to standards and the adoption of new technology, creating successful companies. A native of Baltimore, Maryland, Dr. Soley holds bachelor's, master's, and doctoral degrees in computer science and engineering from the Massachusetts Institute of Technology. I'm Mark Hosky, webcast moderator and content manager for Control Engineering since 1994, writing and editing articles on automation, controls, and instrumentation. I've been writing and editing technology topics since 1987 and have a Bachelor of Science in Journalism and Mass Communication from University of Wisconsin-Madison. Before we continue, please take a moment to remind yourself about dealing with the technical issues during the presentation. And now, Dr. Richard Soley.
Thank you, Mark. I appreciate the introduction. So today I'm going to talk about this new revolution, what we call the industrial internet. But I want to put it in context. I want to talk about how this relates to these revolutions we've had before, the industrial revolution, the internet revolution, thus the title on my presentation, on this slide. So moving directly into it, in the next slide, you see a famous quote from Bill Gates in 1999, "A fundamental new rule for business is that the internet changes everything." And certainly for Microsoft, it sure looked like it changed everything. That's why only 5 years after saying, why would I have an internet division in my company that would be like having an electric division in my company, suddenly there was an internet division, and suddenly there was a strong focus on internet technology throughout the company. But I would argue that the internet has not changed everything. While it did disintermediate a lot of industries, or I should say re-intermediated a lot of industries, that there are a lot of industries in which it hasn't touched at all, in which there's been no focus whatsoever. There's been no what I call internet thinking. So let's move back to the next slide and see where we've been and where we have seen change. Certainly I think the most obvious market is listening to music and reading books and so forth. That's completely changed. I just bought a book just before this webinar started and downloaded it to my Kindle, and that's how I intend to read it on my flight home. I love paper books. I grew up with books. I still love spending time in bookstores. But it completely changed the way I buy books. The internet has completely changed the way I read books. And in terms of music, well, I listen to music the same way most people do, off of some sort of computer, whether it's a mobile phone or whether it's a MP3 music player of some other type. Watching movies has changed. My kids, 24 and 26 years old, not really kids anymore, they don't have cable service. They don't even watch television over the air. Everything they watch comes to a nice flat screen TV from the internet. When their internet was down for a day, they were lost. They had to go outside and play. Contacting people has changed. Skype is the obvious example. We depend on the internet. Reading the news, our cities for newspapers have completely disappeared because people read all of their news on the internet. Obviously, there have been changes there as well, and even in making music, not just listening to music. But moving to the next slide, I'm here to tell you that there have been some markets where the internet has had no effect whatsoever. Early in my career, I worked on as an expert systems developer, building artificial intelligence systems to automatically debug various broken systems. And this was one of the biggest projects I ever worked on in those days. It's a Modicon 584 you're looking at. Modicon was a company that made what are called programmable logic controllers, or PLCs. PLCs are used to drive discrete manufacturing processes. Our example was, in fact, General Motors plant that made brake linings in Michigan. Modicon doesn't exist anymore. It's been sold. It was sold several times and is now part of the French company Schneider Automation. But the interesting thing is the way that you used it in 1980, and that's what the diagram is next to that steel-looking case, the Modicon 584 case on the left. That's a ladder diagram. It hasn't changed. The ladder diagram is how you do it 35 years later. The machine looks different because I guess it's got plastic sides now instead of metal, but you program it the same way. 35 years later. There have been some changes in computing technology in 35 years, but not many changes in that box and not many changes in the way you use a PLC to drive a discrete programmable, discrete manufacturing line. Probably more dangerously, however, in 1980, if you wanted to take information from a PLC and connect it to your information systems, that is, connect your operational systems to your information systems, typically you had to print it out, carry it across the factory floor, and type it back into an information system. In those days, we called those systems manufacturing resource planning systems. Today, we call it enterprise resource planning systems, systems like that you can get from SAP or from Google or from Microsoft and so forth. It's still true that those PLCs don't connect directly to the internet. More importantly, they don't connect to our ERP systems. If we want to share information between those two systems, we have to painfully, at best, bring it on a USB key or some other sort of connector cable. But at worst, print it out and type it back in. 35 years, haven't seen any change. Let me give you another example on the next slide, energy management. In 1950, energy grids were designed with the assumption that there were tens of millions or hundreds of millions of energy users, but only a handful, dozens at most, of power generators. And you didn't need to pass information on the grid itself because information was all one way anyway, so that what information could you possibly pass? Obviously, energy grids need to change. So the three grids in the United States, East, West, and Texas, have basically not changed. They still don't pass information. And yet, the nature of the way we generate electricity has changed tremendously. We generate power on the roofs of all sorts of buildings. We generate power from aeolic systems, that's wind generators, from thermal generators where you have volcanoes and earthquakes and so forth, and from tidal generators along the coast. But those generation sources obviously don't have the consistent power output of typical nuclear, coal, or gas power generators, and therefore we have to change the grids to deal with that, but we haven't done so. There have been lots of experiments to build those microgrids, but it hasn't happened yet. Worse, the information that we need to pass around the energy grid in order to make those changes live doesn't exist on the grid itself. I was invited to speak at an energy grid-related event a few years ago where they were complaining that they needed to find a way to communicate information around the grid, and there was a huge amount of information. They didn't know how they were going to accomplish that without changing the grid itself, which can't pass information at all. So I said, well, let's figure out how much information that you want to pass. Turns out it was just thermal information, temperatures, from a couple of hundred sensors around North America, about 1 byte of information every second. So that's 86,400 seconds a day. And only a couple hundred of these sensors. That only comes out to 2 megabytes a day. I looked up to them and I said, well, I don't understand what the problem is. That's only 2 megabytes a day. And they said, yes, don't you see? A huge requirement for data transmission. I said, well, in my house, I have 2 megabytes a second. Swear to God, one of them looked up and said, oh, no, so do I. What's happened is a lack of Internet thinking, a lack of thinking about how the Internet changes things, how the convergence of low-cost connectivity, low-cost compute power has changed the way we can build systems, even though those systems are already computational systems. So there's a case, 65 years have passed without any real change in design of the way those systems are built. Moving on to the next slide, in aviation, one of my favorite examples, because I'm a bit of an airplane nut. Most of you may have heard that jet engines collect information while they're in flight. They can land with many terabytes of information that can be used to figure out whether they were performing at peak performance, whether they can be made more efficient, how much fuel they use, whether there's a bent fan blade in the second stage compressor, all sorts of information. You'd think that since every airport in the world has Wi-Fi, the airplane would simply connect to Wi-Fi after landing, upload the engine information. That would go directly to the engine manufacturer, whether it's Avic or Rolls-Royce or Pratt & Whitney or General Electric or CFM or whomever. They would then benchmark that data, big data, against the use of that engine on that wing, on that type of airplane over the last 40 years, and say, you know what, this engine's about to fail, or maybe we can make it more efficient if we go replace one fan blade, or maybe we need to change the fuel mix. In fact, none of that happens. Although there have been instrumented engines since 1950, still here in 2015, if you want to get that instrumentation information off the engine after the plane has landed, somebody's got to stick a USB key or a cable, more likely a cable, into the engine, download the data, look at it maybe at the end of the shift and see whether some of it ought to be sent up to the jet engine manufacturer. The engine manufacturer, perhaps at the end of the week, might run against benchmarks and say, oh my God, we better go find N5227 because it's about to fall out of the sky. 65 years, no change. Obviously, there are some changes we can make here. Moving on to the next slide, I see this as a transition very much like the last two revolutions. In the late 19th century, we had the Industrial Revolution. The Industrial Revolution featured the move from human brawn to machine brawn. There was, of course, a social disruption that came with that, as people were kicked off the looms and replaced with steam-driven looms, and then later internal combustion engines, and then later electric engines. That's what led to the Luddite movement, especially in the textile business. People who had been cast out of their jobs or would soon be cast out of their jobs, destroying those new electric looms and complaining about it. But in fact, in the end, far more jobs were created than lost. Of course, they were different jobs. So there was a social disruption, but there was an enormous increase in productivity. Look at the chart to the right. You can see the estimated productivity jump. Global GDP per capita jumped by somewhere like 4 to 5 times because of the Industrial Revolution. We saw that happen again in the late 20th century with the introduction of connectivity by computers, taking away connectivity problems from people and moving into computers, and compute power as well. And with it, a concomitant enormous leap in productivity again. The Internet revolution resulted in something like 2.5 to 3 times productivity jump, as you see in the chart to the right. We think if you take Internet thinking and add it to those industrial systems, you get Internet, the industrial Internet. And that's where our focus is in the Industrial Internet Consortium. Again, we think there will be an enormous jump in productivity, an enormous jump in global GDP. What we're specifically looking at, as it says in the next slide, is disruptive technologies to lead transformational change. There will be social disruptions. Disruptions that cause transformational change cause disruptions in the way societies are organized. Clearly, we're going to see, for example, in a world of self-driving cars, especially when the self-driving cars talk to the roadbed and talk to each other, we're going to see a world in which taxi drivers need to find a new job. That's what we mean by disruptive. That kind of disruption makes changes that change the world. But that's our job, is to find those transformational changes and make sure that we can make those transformational changes without destroying our own industrial basis. In the next slide, we map out the difference between what we call the industrial Internet and what we call consumer IoT. So the Internet of Things is a basically simple idea. It's the idea that we take information from thousands, tens of thousands, potentially even millions of sensors worldwide. We integrate that information and we run it through big data. That is, we do predictive real-time analytics on that data and see when something or when something can be made more efficient. And we take that back out either to human beings or, ignoring human beings completely, go directly to actuators positioned around engines or power generators or anything else that's manufactured. So we're not talking about Fitbits, we're not talking about shopping carts, we're not talking about self-driving cars. While those are important markets, our focus at the Industrial Internet Consortium and what we call the Industrial Internet of Things is in transportation, it's in manufacturing, it's in electric power generation, distribution, and transmission, it's in oil and gas oil and gas exploration, distribution, and so forth. That's where we need super robust systems. We need security around those systems. That we call the industrial internet. Where are the opportunities? In the next slide, you see where some organizations have tested the size of the opportunity. General Electric's chief economist, a gentleman by the name of Marco Annunziata, about 4 years ago published a paper called The Industrial Internet of Things, in which he calculated the impact of the industrial internet on world GDP and figured that about 46% of world GDP ought to be affected by changes that come from applying the Internet of Things to industrial systems. That's a $32.3 trillion annual opportunity. Think about it, a 1% swing, and we're only looking for a 1% swing at first. In $32.3 trillion, a 1% swing is $300 billion. And in fact, Gartner says they expect a $300 billion revenue, incremental revenue, starting by about 2020. Cisco says it's going to add 19 trillion to the global economy by 2020. McKinsey jumps in and says it's a $36 trillion operating cost decrease by industries affected by IoT. The convergence of these ideas, the Internet of Things, Industrie 4.0, Industry 4.0, industrial internet, cyber-physical systems, is an enormous opportunity. Where does that come from? In the next slide, I talk about how we make sense of those numbers. The most obvious example is revenue generation. There are revolutionary new products and services, most obviously services. The Industry 4.0 program in Germany just published an excellent paper on this topic called Smart Services Welt, Smart Services World. A good example, for example, is GE's jet engines. If you go to GE and buy a jet engine from them today, you can buy it the old-fashioned way and then buy parts for the next 30, 40 years. Or they will lease it to you. They will lease it to you on the basis of propulsion as a service. They'll sell you a certain amount of hundreds of thousands of pounds of propulsion for a certain number of hours, and they'll guarantee fuel use. More than that, they will guarantee that fuel use will drop by 1% per year as long as the lease goes. And if you break that fuel, if the engines break the fuel use promise, they'll pay for the extra fuel. They're depending on the fact that, unlike in previous days, they will have direct information from that engine. They will know what's efficient and what's not efficient. They will maintain that engine better than anybody else could do that because they design the engine and they have real-time information about the engine's performance, and they have predictive information about that engine because they have millions of hours of information about that engine on that wing on that kind of airplane. Those new operational efficiencies will drive down costs, obviously, as well. GE is depending on that in order to lease their engines and have the fuel use promise drop every year. And that will increase customer satisfaction as well. I think we're aiming towards a time 20 to 40 years from now where products simply don't fail. Or if they're going to fail, we get a spare part or a replacement in the mail before they fail, because the manufacturer has that intimate, direct, continuous connection to the product. It's not sold to a distributor and then sold to a wholesaler and then sold to a retailer. At least the manufacturer knows how it's being used, knows more about what kind of product to build next time, and knows how to make sure those products stay in operating and peak efficiency. What are the size of the opportunity? In the next slide, I've copied some numbers out of Marco Annunziata's paper again. I think those first couple numbers are really the most interesting. $30 billion in fuel savings over 15 years. $2 billion a year in fuel savings. I'm ensuring that those engines are more efficient. That's only General Electric engines. $66 billion in fuel savings on the gas-powered fleets of General Electric's gas engines. Over on the right there, $53 billion productivity improvement in healthcare. And let me be clear, some of that is because of lower liability, but also some of that is because of lives saved. In addition, reduction in CapEx in oil and gas exploration development, a lot of that CapEx moving to operational expense because of the leases that I've talked about. So how do we get to this beautiful world? I hate presentations in which they say the future is so bright we're going to have to wear sunglasses. So I won't say that. But I will say, to get to that future where we have products that no longer fail, we need to have all these different players, as I show in the next slide. The connectivity providers, the government organizations, the industry organizations, the big data providers, research and academic organizations, standards organizations, open source organizations. We need them working together. We can hope that that will simply happen. We can hope that they'll talk to each other on a one-to-one basis, as I show in this slide, and they will get to the point where they're sharing enough information that we get to industrial internet fast, and then we get those savings fast. But we don't think that's actually going to work. Our view is, as I show in the next slide, if we had government players and industry players and connectivity players and technology players and research players and academics and so forth working together in an industrial internet consortium, we could actually test bed these systems, build prototypes, find out what works and what doesn't work. Sure, standards are going to be a limiting factor, but we don't know what standards to build yet. I have more than 30 years of experience in the standards world. I love standards. Standards are the greatest source of innovation in the world today. But when you don't know what standards to build, you've got to go find it out. So let's go find those new disruptive products and services. Let's figure out what will transform business, and let's do it together. So what the Industrial Internet Consortium provides is a collaborative environment to design test beds. And I'm going to talk about a couple of those test beds. But first, let me just clearly spell out in the next slide the mission of the Industrial Internet Consortium. As you see, accelerate growth of the industrial internet. We know it's coming. Look for the disruptive new products. Integrate those things, those objects, with people, processes, and data. And find, these are the most important words at the end there, transformational business outcomes. We're not doing this because it's cool technology. We're doing it because we think it's going to transform business. We need to find what those transformations are, what those disruptions are, what those disintermediations are, and prepare for them now. Not only from the social perspective that governments should be looking at, but from the industrial perspective so that we know what to do with our own business. After all, it's better to cannibalize your own business than to wait for somebody else to do it for you. On the next slide, I'd like to mention just a little bit about our membership. The Industrial Internet Consortium has grown at an incredible clip. There were 5 founding industrial players. We expected to have about 50 members by the end of 2014, but instead there were about 120, and today there are about 170. So these numbers are approximate. I can't keep up, and especially since I travel. As you see, a lot of large companies, about 50 in total, more than 50 at this point. More than 75 small companies. So small companies are going to have impact on the industrial internet world as well. Small companies can bring different kinds of innovations to the table than large companies can. And it's critically important that not-for-profit, academic, standards, open source, and laboratory testing organizations participate as well. Let us know what can be built, what can't be built, what can be tested, what can't be tested, and so forth. If you're interested to see whether your organization is already a member of the Industrial Internet Consortium, just go to iiconsortium.org and you can find the list of members there. So our process is pretty straightforward. Our process is we bring together the ecosystem, we give them rules of the road for how to collaborate. We build shared technology approaches. We call that a reference architecture. We've just finished our reference architecture. We're going to be publishing it shortly. A security reference architecture, a set of use cases and security use cases, and we use those to drive the development of test beds, prototypes, demonstration projects, again, to find the transformational business outcomes. As you see in the IIC core focus area slide, the net result is, we hope, and we're pretty sure we're going to get to innovative products. In fact, our first test bed has already had some positive results. In the next slide, you see the IIC track and trace test bed. 3 primary companies have driven that, especially a German manufacturing company, an American connectivity equipment maker, and a large Indian systems integrator. Built a solution which we call track and trace. It's quote, only a demonstrator, unquote, but as I say, we've already had some positive results. Moving on to the next slide, the IIC testbed track and trace. The idea of this track and trace testbed was quite straightforward. The idea is if you can track all of the tools, people, parts, and inventory flowing through a manufacturing site, you can make sure that that site is much safer, that people are only using the tools that they're supposed to be using and trained to be using, to make sure that the tool is being used on the right piece of inventory and with the right part, and that the bolts are tightened the right way. But also you can make your factory floor more efficient because you know the flow of products, inventory, work in progress that's flowing through the that's flowing through the factory. So you can monitor and control quality and increase quality, and therefore increase, obviously, customer satisfaction as well. This two-phase project is actually coming to an end. The first phase is coming to an end today, and already there are results on that have generated changes in the way manufacturing is done in some manufacturing sites. It's generated a large open source project that will be carried out by the Eclipse Foundation, a member of the Industrial Internet Consortium. And it's also generated some important requirements for new standards in how you manage devices in an industrial Internet of Things. Those standards are now being worked at the Object Management Group. A second test bed started soon after that one. That test bed is called Communication and Control. There's a quick picture there, but I think the next slide after this one, IIoT Test Bed Communication and Control for Microgrid Applications, is probably a better overview. Here again, there's an equipment maker, there's a systems integrator involved, there's a maker of high-speed integrated communication software driving this as well. And the goals are to integrate solar, wind, and electric vehicles into microgrids and build better electric power grids than we've had in the past. We talked about power grids earlier in the presentation, so I won't belabor the point except to say if we had microgrids, we could deal with the varying inputs of the varying outputs of power usage in cities and the varying inputs of aeolic, that is wind sources and thermal sources and tidal sources and solar sources and so forth. Share power between grids, move power around as necessary, and have a much more efficient power grid system. This test bed is under development now. There is a test system that's being built in Southern California now. If that works, it will go full scale in a test bed in San Antonio, Texas. And there's much more information about both these test beds on the Industrial Internet Consortium website. Why now? I'm going to wind up by saying, look, what's driving this is not anything particularly new in terms of technology, but low-cost, powerful technology, low-cost processing power, connected everything, big data technology, both in terms of integrating large amounts of data that is well-structured, like engine data, and looking for nuggets of information in large amounts of unstructured data, the way Hadoop does, or Google for that matter. And I think we're headed towards a lot smarter machines, not only in smarter manufacturing and smarter products, but a lot smarter data as well. In the next slide, what about standards and open source? Well, we're working together with approximately a dozen now standards and open source organizations that are involved in the Industrial Internet of Things, that are involved in standardization, that are involved in open source, like the Eclipse Foundation that I mentioned earlier. I think we're headed towards a future, as I mentioned in the next slide, of jet engines that reduce jet engine failure and maintenance costs and even reduce pollution. But my favorite example is the one over on the right-hand side there. For those of you who have never seen that device that's clipped on someone's finger, that's an oxygen sensor or O2 sensor. It attempts to look through the skin and decide how much oxygen is in your bloodstream, because obviously if you drop below a certain level of oxygen in your bloodstream for more than 4 minutes, you don't really need to worry about anything anymore. Unfortunately, O2 sensors don't work very well. They have about a 20% failure rate. And even more unfortunately, ICU, intensive care unit nurses, are well aware of that fact. So if they get an an alarm, from an O2 sensor, they might ignore one or maybe even two, because they know that you've got 4 minutes, and likely if you've got 65 other ICU patients, you've got to look at a lot of different things going on all at once. This despite the fact that if O2 is falling and respiration is falling, you know that there's a problem and you better get in there and do something about it right now. So clearly all you got to do is integrate O2 sense and respiration sense, but nobody does that today. Still in the labs. Why? Because no internet use, no internet thinking, like I started in my presentation earlier. There's no O2 sensor and respiration sensor made by one company or even sitting on the same network or speaking the same protocol. So integrating them and getting approval for that integration is not an easy thing. Not only are we going to save liability costs in the healthcare space, but we're going to save lives. So I'm looking forward to that. I want to leave you with the message that things are coming together. We are getting to the point where we are building test beds. We're learning from the things from those test beds. We are finding new leasing opportunities, new OpEx versus CapEx opportunities. we're finding new transformational business outcomes. And we're finding out that the industrial Internet of Things, the Internet of Things applied to industrial systems, is changing the world. My final slide, where to get more information about us. Things are coming together. We're building the community to collaborate and converging that technology today. Thanks for the opportunity to tell you more about the industrial Internet of Things today. And I'll hand you back over to Mark.
Thanks very much, Richard. I appreciate your time and effort there. Now I'm going to offer you a little bit of information about Industry 4.0. First, what is Industry 4.0? Industry 4.0 represents the fourth industrial revolution with the use of cyber-physical systems. In case you were wondering, the first industrial revolution was use of steam engines. The second was use of mass production and conveyors. The third was electronics and information technology. The goal of Industry 4.0 is to facilitate the emergence of the intelligent factory, which has adaptability, resource efficiency, ergonomics, and integrates customers and business partners, creating value. It was adopted in November 2011 by the German government as part of the Action Plan for High-Tech Strategy 2020. There is a governing organization called Platform Industry 4.0, which aims to help those involved actively participate in the fourth industrial revolution, which is the source of the name, strengthen the German economy, it's a German-based organization, encourage development of standards, business and organizational models, and promote practical implementations with an exchange of technologies across industries. The organization also aims to ensure that Germany is a leading provider by 2020 of cyber-physical production systems. I feel a need to pause and briefly explain why I'm giving this presentation, though I'm not associated with the Platform Industry 4.0 group. I met and invited a member of Platform Industry 4.0 Steering Committee who agreed to speak for the webcast. We changed the date for the webcast, which created a conflict. The organization, which is in an expansion transition right now, was unable to provide a replacement. Therefore, I used information from primary sources cited at the end of my slides to assemble this presentation, just as I would write an article for control engineering or plant engineering. Those involved with Industry 4.0 organization include Bitkom, which is a German Federal Association for Information Technology, Telecommunications, and New Media. That has about 1,400 members in that organization. VDMA, which is a German federation representing about 3,100 companies. And ZVEI, a German Electrical and Electronic Manufacturers Association, representing the common interests of the electronics industry and related service companies in Germany. About 1,600 companies are involved. At Hanover Fair in April, the new Industry 4.0 platform group was announced. It is being headed by a German Economic Affairs Minister, the German Research Minister, with key representatives from industry and industrial associations, the German Metal Workers Union, and the Fraunhofer Society, a German research organization with 67 institutes covering health, security, communication, energy, and the environment. Industry 4.0 platform has working groups covering the following topics: reference architecture, standardization, research and innovation, networked system security, the legal environment, work, and education and training. Some basic concepts for Industry 4.0 are cyber-physical production systems. Use microcomputers as embedded systems where hardware and software components are integrated into comprehensive system to implement specific features. The Internet, mobile computing, and cloud computing have the potential to enable greater productivity for industrial processes. Cyber-physical production systems can be integrated into objects, products, and equipment to exchange information automatically as needed. Industrial processes are not organized centrally, but are decentralized and dynamic using this framework. Smart objects and machines are used in Industry 4.0. Products embed intelligence and inform machines what to do by using barcodes or radio frequency ID chips, RFID chips, with the appropriate information. Scanners and computers read data, transmit, and ensure that machines operate properly. Smart objects communicate with each other, creating the Internet of Things and services. The physical world and the virtual world merge into cyber-physical systems. In the networked factory, Industry 4.0 framework enables production logic to change. Also, intelligent machines and products, storage systems, and resources are interlinked through the Internet along the value chain, including logistics, production, marketing, services, throughout the whole value chain. Here's an example of how Industry 4.0 can be applied. In the automotive automation area, car components collect data about a condition and tell when a replacement is needed before the failure occurs. The product independently sends a message to the manufacturer that replacement is necessary. The order contains detailed information on vehicle types, what is needed, and where the components should be sent for repair. The factory processes the order. Machines automatically configure themselves so that the right part is made and then sent to the correct location at the right time for the repair to occur. Industry 4.0 offers benefits that can be grouped into 5 categories: competitiveness, flexibility, individual or customized production, innovation, and new work capabilities. I'll give some details on each provided by the organization. First benefit is competitiveness. Germany, the organization says, is said to have an internationally leading manufacturing base, strong in the field of embedded systems. That is enhanced with active support of the transition to Industry 4.0, networking of products and equipment, and the efficiency of manufacturing companies help promote global competition. Benefit 2 is flexible production, which helps with international competition. In Industry 4.0, processes are transparent as companies track goods and processes and act flexibly. Processes can be adapted in real time so that production matches delivery quantities as needed. Production processes can be optimized across locations for quality, price, or resource efficiency as needed. The third benefit of Industry 4.0 is individual or customized production, which means that production of single pieces and small quantities can be profitable. Goods can be specified on certain machines sooner as needed using information technology. A product might be painted blue or red on the same machine without any difficult reprogramming. Production reacts quickly to individual customer-specific requirements. The fourth benefit of the fourth industrial revolution enables new business models and services. Intelligent objects collect diverse data, which can be used for innovative services. Startups to medium-sized enterprises with ideas can benefit from big data and more quickly establish themselves with services to offer in their marketplaces. Benefit 5, Industry 4.0 will also help with extreme demographic changes affecting manufacturing. Processes will be tailored to workforce capabilities. Industrial work can be made more flexible to benefit employees who then can make work and family life more compatible. Examples and advice for implementation. Industry 4.0 can use manufacturing IT technologies, information technologies, to create a resilient factory so that production line and processing stations can quickly adapt to a changing market product mix to optimize capacity. Industry 4.0 can improve networking to increase the ability to quickly and easily share knowledge. Industry 4.0 can adjust and optimize part production and processes such as cutting metal parts with lasers by quickly assessing internal and external technology expertise to finish the order on time with the expected quality. More examples might include intelligent maintenance. Costs can fall as predictive maintenance significantly reduces unplanned shutdowns. Greater use of networks in production helps mass customization, adapting to turbulent markets with flexible production processes. Adaptive logistics. Network production can increase reliable production processes for low-friction, error-free, value-added processes. Even as demands for piece number and variant flexibility increase, bottlenecks and errors can be avoided. Cyber-physical systems can make materials and part movements transparent, forming dynamic, intra-logistical controls in a flexible factory. Integrated engineering. As customers demand both functionality and changes, classic production needs rethinking. By integrating customers in development, planning, and value-adding activities, greater transparency and tighter synchronization results for all participants. Sustainability and upcycling versus recycling. As commodity prices increase, better information flow allows the sale of only products used with retained ownership of raw materials used, with appropriate information stored in the product. Smart factory architecture. Product life cycles and factory life cycles can be enhanced and synchronized. Beyond any specific technologies, Industry 4.0 creates value for customers, and none of this happens without cybersecurity. While distributed systems have been around for a long time, significant cybersecurity investments are needed for more real-time information flow and related value. This concludes the information from Platform Industry 4.0. Now I have 2 slides with control engineering research results prepared just for this webcast. As part of the upcoming Control Engineering Research Report on System Integration, we asked subscribers what part of the Industrial Internet of Things technology framework is useful. 72% thought that interoperability and open standards connecting people, processes, and data. 47% said security. 46% said mobile, 29% cloud, 29% analytics, and 2% other. That was with 123 respondents and a margin of error about 8.8%. Similarly, the research asked subscribers what part of Industry 4.0 framework is useful. 55% mentioned real-time capabilities, 47% checked off modularity, 45% interoperability, 39% virtualization, 32% service orientation, 29% decentralization, and 2% other. Obviously, for both of these questions, they were allowed to select more than one answer. And with this one, 87 responses, the margin error is a little over 10%. I'd like to thank Amanda Pelliccioni, Director of Research for CFE Media, for these research results. As a personal observation, when investing in new technologies to help achieve these new capabilities, it's not enough just to apply the new technologies. You have to examine, rethink, and redesign processes with the new capabilities in mind, and then apply the new technologies. So the sources for information on this part of the presentation included Platform Industry 4.0 organization website, notes from the 2015 ARC Forum presentation and comments from Dr. Reinhold Katz, member of the Industry 4.0 Steering Committee, the announcement of Platform Industry 4.0 expansion from the German Federal Ministry of Education and Research and Economic Affairs, and the Control Engineering System Integration Research, which will be available in June along with Control Engineering and Plant Engineering coverage of Industry 4.0. So, on to the questions now. I see many questions coming in, and the audience listening can type questions for today's presenters in the Ask a Question box on the screen. We'll get to as many as we can. Within a few days of the presentation, we'll be available for on-demand viewing, and we'll post the archive on the websites and send you an email with the link connecting directly to it, along with related resources after it's ready. For those of you listening to the archive, stick around for a few minutes, and the Q&A is always fun. For those questions we don't get to, we will post some of the answers online so you can access them with the archive webcast. First question, impact of Industrial Internet of Things on cybersecurity. Yes, that was one of the main points through several of the presentations and in the research. Richard, how does cybersecurity fit in?
That's a great question, Mark, and it's almost always the first question I get asked, that and standards. Obviously, if we get, as one person said to me after giving this presentation in Berlin a few months ago, he said, if you give me the same level of security on my manufacturing systems as the internet world has given me in social applications, I'm a dead man. And clearly, we have to deal with that problem, and it hasn't been dealt with. I mean, we're taking advantage of the fact that internet technology is cheap and pervasive. But we're going to have to make sure that those systems are secure. So at the Industrial Internet Consortium, our focus is building security in from the start. So we've had from the beginning a security working group which defines its own use cases and applies those use cases by our rules to every test bed that we develop to make sure that we have solved the problem of making those systems as secure as possible, both from external threats and from internal threats. Will there be successful attacks? The answer is yes, just like there are successful attacks in the real world. But we're taking the security problem very seriously, and we do expect those systems to be far more secure than the internet is today.
Great. How do you overcome advice on inertia, getting to where we need to be with Industrial Internet of Things concepts?
I'll give you some advice on that. The reality is, like any technology trend, there's a bell curve. There are early adopters. There's the great bulk of adopters in the middle, and then there's the late adopters. In this case, the late adopters will be out of business. The changes, the disruptions that are coming from this technology are so great that they will completely change the way that some industries work. I mean, I didn't talk much about the elevator industry, but there is an elevator company that failed to provide the kind of real-time predictive maintenance for their elevators in time to keep from another small startup company from providing that same information on their elevators and basically taking over the lucrative repair and resupply job for the elevators made by this manufacturing company, and threatens their very existence. So my advice is, I hope that you believe that this is disruptive and transformative, and I also hope you believe you're not going to figure out all the possible disruptions and transformations to your industry. So get involved now in figuring out what those disruptions and transformations will be, so that you can have some hope of cannibalizing your own business rather than having somebody else do it for you.
That's great advice, Richard, and we have a lot of other great questions here. Richard has offered to answer some offline, as I will. We will get those posted with the archive version. Thanks for the good information, and for our great speaker, Dr. Richard Soley, for sharing his time and expertise. And thanks to the Platform Industry 4.0 for the information used in this webcast. We'll link to the related resources from the archive area.